Welcome to part 3 of chapter 11. Today, we are going to continue our discussion of stoichiometry by learning 2 new applications. The first one will be on solution stoichiometry. This will use molarity as a conversion factor so that we can measure out amounts of liquids and determine how many moles of our substance are in that liquid. And then we can use, our mole ratio to convert between substances, just like we've been doing. So the key for solution stoichiometry will be using molarity as a conversion factor. The other type of stoichiometry that we're covering today is gas stoichiometry, and that will use the molar volume of a gas at STP as a conversion factor. So we'll get to that in a little bit. So let's get going. All right, like I said, our first topic is going to be on solution stoichiometry and this idea of using molarity as a conversion factor. We already learned how to calculate molarity in a previous chapter, but now we're going to take that molarity calculation and apply it to stoichiometry. This is going to be super similar to previous stoichiometry problems that we've done. Like all of the, kind of canceling things out, the train tracks, all of that is going to be exactly the same. We're just using one new conversion factor, and that will be molarity. Like we learned before, molarity shows the relationship between moles of a substance and liters of that solution. This is super useful in chemistry because a lot of times we will be measuring out a liquid. We've done this already in lab. This is very, very common. And if you look closely at the bottles that we use in lab, those reagent bottles, they will say a molarity on them because that's a really common way in chemistry for us to describe how much stuff is dissolved in our solvent. Okay, so molarity is the most commonly used concentration unit in chemistry because it allows us to relate things to moles. And that is really useful for stoichiometry because it allows us to directly use that mole ratio. Let's say, for example, there was a sugar solution sitting on the back counter, and it says on that bottle that the concentration is 2.0 molar. Okay, that is our unit for molarity. This capital M stands for molarity, and it's pronounced molar. So that is telling you that for every 1 liter of solution, there will be 2 moles of sugar. Okay, so we can use this as a conversion factor. We can say, okay, for every 2 moles of sugar, there's 1 liter of solution, or for every 1 liter of solution, there's 2 moles of sugar, right? Essentially, the way that it plays out is that this 2 molar that we see here, that's saying 2.0 moles is equal to 1 liter. And remember, when things are equal, they get stacked in these train tracks. So this 2.0 molar says, okay, for every 2 moles, that will be 1 liter of solution. And then, you need to figure out whether it goes on the top or the bottom, depending on how our units are going to cancel. Alrighty, let's go ahead and do an example problem. This one says how many milliliters of a 0.175 molar mercuric nitrate are needed to react with 2.50 grams of potassium iodide. So this is a reaction. So the first thing we're going to need to do is write a balanced chemical equation. You'll see that I've given you the 2 reactants, right? We have potassium iodide and mercuric nitrate, but I didn't tell you what it makes. After the last chapter, you should be able to write balanced chemical equations. These are 2 compounds, so this will undergo a double displacement reaction. You need to be able to predict the products of this reaction and then balance it. For now, though, let's just go ahead and write it down. So here's our reaction, and it's balanced. Okay, we are going to start our train track with grams of potassium iodide. But when you're looking at this, you may be thinking, okay, well, how do we know which thing to start with, right? Usually in a stoichiometry problem, we just go and find whatever number is in the problem, and we put that in the beginning of our train track. But you'll notice here we have 2 different numbers now. We have a molarity and we have a mass in grams. And so the question is, which one do we start with? You are never, ever, 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 ever going to start your train tracks with molarity. I'm going to say it again. You will never, ever, ever start your train tracks with molarity. The reason for that is that molarity is a conversion factor. So let's take this here. 0.175 molar. So that, if we think about that as a conversion factor, that's going to tell us 0.175 moles is equal to 1 liter. Whenever you have a molarity, that number is always going to go with moles. It's always going to be 1 liter, because if we think about it, right, molarity is moles over liters. So this is telling us this is 0.175 moles over 1 liter. Okay, that's the technical definition of molarity. So if we were to separate that out, we're seeing 0.175 moles is equal to 1 liter. Or you can think about it as the fraction, either way. But molarity is a conversion factor, so we cannot start a train track with molarity. Hopefully I've said that enough times. All right, so that means we have to start our train track with the 2.50 grams of potassium iodide. So there it is. Remember, in order to change compounds, we always need to turn this into moles. So right now we have grams. So in order to turn grams into moles, we are going to use the molar mass. The molar mass will go on the bottom because grams has to cancel grams. And the molar mass is always equal to 1 mole, so that's what goes on the top. Once we convert grams of potassium iodide into moles of potassium iodide, then we can change compounds. And the way that we change compounds is we use the coefficients from the balanced chemical equation. So we go and we find potassium iodide. If you look there, potassium iodide has a 2 in the front, so that's going to say for every 2 moles of potassium iodide, we will need 1 mole of mercuric nitrate. Okay, since this is asking how many milliliters of mercuric nitrate, that's why we're changing into moles of mercuric nitrate here. Okay, once we have that all canceled, now we need to go about solving the question, right? This says how many milliliters. In previous stoichiometry problems, we were usually, from here, turning moles into grams so that we could weigh our product. But this says how many milliliters, implying that this is a solution, not a solid. So oftentimes we measure out solutions in milliliters, right? We use a graduated cylinder. So we will use our molarity as a conversion factor to convert this into milliliters. So you'll notice though, in our conversion factor, right, molarity is moles over liters. So we'll first convert this to liters and then we can convert it to milliliters. All right, so if we are going to use molarity as a conversion factor here, we are going to use this. 0.175 moles is equal to 1 liter. Remember, our units have to cancel down and to the right. So that means that this portion of our molarity needs to go on the bottom, and that 1 liter will go on the top. Okay, we'll make sure our units cancel. And then, had I just asked for liters, you could stop here. But in this particular question, I asked for milliliters. So we are going to go ahead and convert our liters into milliliters. If you've forgotten, remember that 1 liter is equal to 1,000 milliliters. This is one you should definitely have memorized. We use this conversion factor all the time in chemistry. Okay, so we're going to go ahead and use it here. So again, our units are going to cancel down and to the right, so liters will go on the bottom and 1,000 milliliters will go on the top. Make sure our units cancel. And now, since we've found milliliters of mercuric nitrate, which is what we were looking for, we can multiply all of the numbers on the top, divide by all of the numbers on the bottom, and get our answer. Okay, so this was pretty long. This is probably the longest stoichiometry problem we've done so far, but hopefully you can follow the logic. We started with grams, and we used the molar mass to turn grams into moles. Then we used the mole ratio to change compounds. Remember, that is coming from the balanced chemical equation. Our new step is here. This is the only thing that was really new today, and that was using molarity as a conversion factor. Remember, the number is always going to go with the word mole. It doesn't matter whether the word mole goes on the top or the bottom. That number that's associated with molarity always goes with the word mole, and 1 liter is the other piece of that conversion factor. Then we turned liters into milliliters and wrapped up our problem. Just like any other stoichiometry problems, we always need to have a number, a unit, and a chemical. Alrighty, let's go ahead and try one. This says how many grams of silver chloride will form by adding enough silver nitrate to react fully with 1,500 milliliters of 0.4 molar barium chloride solution. All right, so this is a lot of information, okay? Let's figure out what the problem is actually asking. So this says, how many grams of silver chloride? So that's what we are going to be trying to find. You can kind of think about like blah, 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 right? This will form by adding enough, right? It doesn't matter. If we were writing the chemical equation, then that pieces of information would be useful because we would need to say, okay, silver nitrate is reacting with barium chloride. But since we're really only, we already have this balanced chemical equation, so we're really only concerned with the pieces of information that we need to solve the problem. So this is all just kind of extra information, okay? So the other things that we have are 1,500 milliliters of a 0.4 molar barium chloride solution. Okay, so thinking about this, remember you are never going to start with molarity. Molarity is a conversion factor, so we cannot use that to start our train tracks. That means we are going to start with 1,500 milliliters of barium chloride. So if you think you can tackle this, go ahead and pause here and give this a go. If you'd like to watch me go over it, then just kind of hang on through the pause and we'll go over it in just a moment. Alrighty, so again, we are solving for grams of silver chloride, and what we're kind of given is 1,500 milliliters of 0.4 molar barium chloride. Again, we are not starting with molarity because molarity is a conversion factor. That means we are going to start our train track with 1,500 milliliters of barium chloride. Okay? In order to use molarity as a conversion factor, we need to have this volume in liters. Right? Because remember, this 0.4 molar barium chloride is going to be 0.400 moles is equal to 1 liter. So we can't use that conversion factor while we still have milliliters. So our very first step will be to convert milliliters into liters. Remember, our conversion factor here will be 1,000 milliliters is equal to 1 liter. Also, if you are really good with this molarity to liters conversion, you don't need to show that as part of your train track. You can say, okay, I recognize I need to divide by 1,000 and I'll just start my train track with 1.500 liters. That's fine. But if math isn't your strength or you're not sure whether to multiply or divide, never guess. Just go ahead and make the train track. I know it's one extra step, but it's worth it to get the problem right. So 1,500 milliliters of barium chloride. We know that milliliters has to cancel milliliters down and to the right, so 1,000 milliliters will go on the bottom and 1 liter will go on the top. So we can cancel out our units here, and we're left with 1 liter of barium chloride. Now we can use our molarity to convert liters into moles. Remember, we always need to convert things into moles in order to be able to use that mole ratio to convert between compounds. So that's what we're doing here. We're converting milliliters to liters and then liters to moles so we can change compounds. All right, so our units have to cancel down and to the right. So 1 liter will go on the bottom and that 0.4 moles from the molarity will go on the top. Our units cancel and now we've got moles of barium chloride. So now that we have moles, now we can use the mole ratio to change compounds. So we look at the balanced chemical equation and we see that there's just 1 barium chloride. So that's telling us 1 mole of barium chloride. Now we're trying to figure out how many grams of silver chloride. So we'll use silver chloride for the top. So that's 2 moles of silver chloride. Make sure our units cancel. And then we notice that our problem is asking for grams. So anytime we're trying to solve for grams, we are going to need to use the molar mass. So finishing up our train track here, that 1 mole is going to go on the bottom and the molar mass will go on the top. Then we can make sure our units cancel and multiply all the numbers on the top, divide by all the numbers on the bottom, and we'll get our answer. So again, this is another example of using molarity as a conversion factor. In the previous problem, we used it at the end because we were trying to find a volume solution. Here, we were using it at the beginning to turn our volume into moles so we could, find grams of our product. So it doesn't matter whether it's at the beginning or the end, it's just another conversion factor that allows us to convert from liters into moles so we can use that mole ratio. Alrighty, go ahead and pause here and complete problems number 33 to 39 on the Chapter 11 lecture worksheet. Once you're done, come back and we'll keep going. Alrighty, our last application of stoichiometry will be on gas stoichiometry. We already covered a whole chapter on gases, and I think gas chemistry is really interesting. A lot of times we will use gas stoichiometry to know how much of a gas should be produced during a reaction. Okay, usually, like we found out before, our volume of gases are compared at STP, right? That's standard condition. So our standard temperature is exactly 0 degrees Celsius, which is 273 Kelvin. And our standard pressure is exactly 1 atmosphere, or 760 millimeters mercury, or 760 torr, or 101.325 kilopascals, right? All of those are equal. So what's really cool about STP is 1 mole of any gas will occupy the same volume. It doesn't matter what the gas is. If we have 1 mole of a gas at STP, then our volume is always going to be 22.4 liters. That's kind of cool, right? The particles of the gas themselves are so small that it doesn't matter the molar mass of our gas or the size of that particle. It all ends up being due to collisions. And so if we have 1 mole of a gas at the same temperature and pressure, they're all having the same amount of collisions and therefore giving us the same volume. I think that's pretty cool. So this gives us a new conversion factor. 1 mole of any gas is equal to 22.4 liters. So after we learn about gas stoichiometry, you will now be able to do all types of stoichiometry problems, which is pretty cool. In the first lecture, we talked about how to convert atoms or molecules into moles and then use that mole ratio to convert between compounds. We also know how to use grams to go to moles, and that would be using the molar mass. We were just talking about how to convert the volume of a liquid into moles using molarity and then, using the mole ratio. Now, though, sometimes we have volumes of a gas, not just volumes of a liquid. So if we have the volume of a gas, then we will use 1 mole of a gas is equal to 22.4 liters. So be very careful when you are solving problems involving liters. You need to ask yourself, is this a liquid or is it a gas? If it's a liquid, in order to convert between liters and moles, you're going to need to use molarity. If it's a gas and you're converting between liters and moles, you will use 1 mole equals 22.4 liters. So this volume piece is kind of tricky. So you'll need to use critical thinking and see, is it a gas or is it a solution? Okay, so at STP, the molar volume, right, 1 mole equals 22.4 liters, can be used as a conversion factor to convert between moles and volume. Super cool. So that conversion factor can be used as 1 mole over 22.4 liters or 22.4 liters over 1 mole. You'll notice that this says STP all over it, okay? If you are not at STP, then 1 mole does not equal 22.4 liters. It'll equal some other volume, okay? It only equals 22.4 at STP. In this class, we are not going to solve stoichiometry problems that are not at STP, so you don't need to worry about that in this class. But if you do go on to higher levels of chemistry, you need to make sure that if you're using this 1 mole equals 22.4 liters, that you are at STP. If not, you're doing the problem wrong. So that's why you keep seeing that all over the place. All right, so let's go ahead and try this out. This says, calculate the number of moles of phosphorus needed to react with 4 liters of hydrogen gas at 273 Kelvin and 1 atm. So this should stand out to you as STP. But again, in this class, I am not going to have you do gas stoichiometry when we are not at STP. So you can pretty much guarantee it's always at STP, even if it wasn't mentioned. Okay, so now let's go ahead and figure out this problem. So the only problem, or the only piece of this problem that we really need is this 4 liters of hydrogen gas. Okay, it doesn't matter for our problem that it's 273 Kelvin and 1 atm. all that's telling you is that it's at STP, and therefore we can use 1 mole equals 22.4 liters as a conversion factor. Okay, so we're going to go ahead and start with 4 liters of our gas because that's what we're given in the problem. So we'll start with our 4 liters, and we need to convert this liters into moles. Because this liters is of a gas, we can use 1 mole equals 22.4 liters. Just be very careful. If this, 4 liters was a solution, we would need to use the molarity to convert to moles. So this is something that trips people up. Okay, they see liters and they're not sure, should I use molarity or should I use 22.4, right? Remember, if it's a liquid, right, if it's a solution, you'll use the molarity. If it's a gas, you'll use 1 mole equals 22.4 liters. So since this is a gas, we will use 1 mole is 22.4 liters. Remember, your units always cancel down to the right, so our liters will go on the bottom and 1 mole will go on the top. So now our stuff about hydrogen cancels, and we can now convert into moles of phosphorus, which is what we're trying to find. Okay, so if we look at our balanced chemical equation, there are 6 moles of hydrogen and just 1 mole of phosphorus. And we'll make sure our units cancel. You'll notice here that our problem just said moles of phosphorus. It didn't say grams, it didn't say anything else. We're just converting to moles, so this is where our train track ends. We don't often end at moles, but in this particular problem we do. So now that we've solved for what we're looking for, we can multiply all the numbers on the top, divide by the bottom, and we'll get our answer. Alrighty, I want you to try one. This says calculate the volume of hydrogen gas produced from the reaction of 3.29 grams of aluminum with excess hydrochloric acid at STP. Okay, so you're going to start your train track with the only number in the problem, 3.29 grams of aluminum. And go ahead and see if you can work out how to get the volume of hydrogen gas that will be produced at STP. So pause here, give it a go, and come back when you're ready to see the answer. Alrighty, so we are starting with 3.29 grams of aluminum. Just like any other time, when you see grams, you should automatically think, oh, I need to use the molar mass and convert it to moles. So our molar mass of aluminum will go on the bottom, and 1 mole of aluminum will go on the top. Now that we've converted grams into moles, we can use our balanced chemical equation to change compounds. If we go find aluminum here, right, we have 2 moles of aluminum, and we are trying to find out information about hydrogen gas. So that means hydrogen will go on the top. So that's 3 moles of H2. Make sure our units cancel, and now we can move forward. So this says the volume of hydrogen gas at STP. Remember, if we are finding the volume of a gas, that means we will be using 1 mole is equal to 22.4 liters as a conversion factor. So our units have to cancel, so 1 mole will go on the bottom, and our 22.4 liters will go on the top. Make sure our units cancel, and then we can multiply all of the numbers on the top, divide by the numbers on the bottom, and we'll get our answer. Alrighty, this is actually the end of Chapter 11. You do have a few more practice problems. Those are numbers 40 to 46 on the Chapter 11 lecture worksheet, but you are done with Chapter 11. This is the end of stoichiometry. I hope you've enjoyed it. I really enjoy stoichiometry. I think it's very methodical and logical, and I like that it has a lot of applications in lab. I know it's a math-based chapter though, so make sure you are doing all of these practice problems and then maybe go through and do them all again. If you get stuck at any point in time and you're not sure how to do a particular problem, please make sure to reach out. I am more than happy to help. I really do enjoy stoichiometry, so if you need anything, please shoot me an email or, contact me on Remind or attend my office hours, however you want to get a hold of me, but do reach out and I'm more than happy to help. Otherwise, keep working hard and I will talk to you guys next time.